All right, so let's talk about the properties of superconductors. So we'll talk about our high temperature superconductors, but also just superconductors in general. So to start with, um, we just want to all get on the same page. So let's see the basic properties that make something a superconductor. So it has to have basically two properties. The first is zero resistivity. And so that means there's no resistance to the flow of electrons, and so there is virtually no losses in current, electrical current. So that's obviously important for electronics. The second is that it's going to have zero magnetic flux density, and that variable we call B. And so the way this manifests itself is that if that superconductor is placed in a magnetic field, so next to a magnet or something like that, it appears to reject or ejects the magnetic flux, and therefore it acts as a perfect diamagnet. And so we're going to talk a little bit more about both of these. All right. So superconductors don't possess these properties at all temperatures. Otherwise, everything in the field of electric conductivity and so forth would be solved. We have no losses. There's nothing to talk about, right? So the superconductors only possess this below a certain temperature. And because that is a critical temperature, we call that the critical temperature, so T sub C. So this is the temperature below which the resistivity goes to zero, and then also the magnetic flux density goes to zero. So all classes of materials can exhibit superconductivity. So metals, ceramics, and also polymers as well. However, the temperatures of this critical temperature are not practical for all of these classes. For example, metals were the first to be discovered to have superconducting properties, but as you can see here, the temperatures are less than 10 Kelvin. So very low temperatures. So we'd have to go to extremely low temperatures to be able to experience this superconductivity. And so these aren't practical materials, right? There's not a lot of ways to get down to 9.2 K. All right, so that's where we come up with the designation of a high temperature superconductor. And so we've used the term high temperature to describe a lot of things in this lab. So, at various times it might have been 500 degrees or 850 degrees Celsius, right? So that's oftentimes what we think of as high temperatures. But for superconductors, that distinction is obviously a lot lower. And so for superconductors, a high temperature superconductor is anything with a critical temperature above the boiling point of liquid nitrogen. So this is why I had you look it up in the pre-lab. And so at that point, again, the resistivity goes to zero. And so the maximum temperature for this critical temperature now is on the order of 203 K. But this is also under a fairly extreme pressure, as you can kind of see here. And so at normal pressures, atmospheric, 1 atmosphere, it's 138. So you can still tell that it's a pretty low temperature, well below room temperature, right? And so the ultimate goal would obviously be to get something with a critical temperature at or near room temperature. That's the ideal scenario of what we can have here. All right, so as you might expect from the lab that we're doing, we are making a ceramic. And so this ceramic can be a superconductor. Even though our general properties of ceramics, we tend to think of them as insulators. But even they can be superconductors at low temperature. And so back in the 1980s when this was discovered for ceramics, it was a big breakthrough, and there's a lot of research that happened. And so same thing with a couple different ceramics here, is they act as perfect conductors, have zero resistance. This is a resistance versus temperature plot, and you can see the temperatures here are above the boiling point of liquid nitrogen. So we're close to 90 and close to 110 K. So ceramics have relatively high critical temperatures compared to the metals that we saw before, where we're closer to 10 Kelvin. Okay, so the other part of this, besides the resistivity, is also the magnetic flux density, which we call B here. And so for superconductors, this is 0. And so this is a formula for magnetic flux density, but more importantly, just to think of it conceptually, if the induced magnetization, which we call M, so this is within the within our material, so in this case our superconductor, that opposes the applied magnetic field H, right? So the applied magnetic field is again applied by a magnet or something like that, and so it exactly opposes the applied magnetic field inside the superconductor, and therefore B in this equation is going to go to 0. As it turns out, there's also two types of superconductors, type 1 and type 2. Type 1 is where we can, where that is completely proportional. The induced magnetization opposes the applied until a certain point in which, so a critical value of the applied magnetic field, and then that goes to 0. So that effect, once you pass a certain level, goes away. So that's what you can see here from this graph. So at a certain point, that just sort of fails, and so it can no longer oppose the magnetic field. And the other type, type 2, which is actually what ceramic superconductors are, is where it gets to a certain point and the effect is actually lessened. And so you have kind of a mixed state above a certain value of applied magnetic field, and so the how much it can oppose actually goes down. And so it's not always an ideal magnetic flux of 0 in those cases. All right, and so because of this magnetic flux density being 0, like I mentioned earlier, this has a result of making superconductors perfect diamagnet. And so what that means is that normally the applied magnetic field would go through our sample, like we see here. So when it's above the critical temperature, it just goes through the material. But below that temperature, it opposes that magnetic field, and so we think of that as expelling from the field. And so it has this expulsion of that field below this temperature is known as the Meissner effect. And so you've probably seen this one. This is the one that has all the nice pictures and so forth. So in the top here, the top image here, I'm showing a superconducting pellet. And it's in liquid nitrogen, so it's below the critical temperature. And above that, levitating, is a magnet. And it's levitating because it's expelling that magnetic field, and so that results in a force on the magnet to repel it from the superconductor. And so that's what we know as the Meissner effect. And so applications, maglev trains, those are sort of applications of this, using that perfect diamagnet property that superconductors have. And so this is something we'll also see through the lab. All right. So how does it do all of this? How does it get its superconducting properties? And so for that we turn to theory. And most of the early theories revolved around metals. So how superconducting properties happen in metals. And so that's what we're going to go through here. So this is known as BCS theory. And this is for the low temperature superconductors. So it's much more well known or explained in these low temperature superconductors, less so in the high temperature. There's still a lot of work going on in explaining how that happens in high temperature superconductors. So, but I thought we'd go through this and see how it happens in these low temperature superconductors. So for this theory, imagine that you have a metal. So you have the crystal lattice here, and you have free electrons. So we're going to look at one free electron here, right? So as that free electron is moving through a metallic lattice, if you think about it, this free electron, is negatively charged, right? And so then we have all of these positive ionic cores of the metal, right? Because the free electrons are floating around, so the core left over is positively charged. So momentarily, when the electron is near these positive cores, those positive cores are going to be very slightly distorted towards and attracted to this negative electron, right? So it's attracted to that negative electron as it moves through. So what that does is, now if you sort of envision this whole radius here, so this whole thing I've highlighted in red, so where we have a free electron and the positive cores are slightly moved toward that free electron. So if you are another free electron, what you see in that vicinity is something that has a positive charge density, right? Because that free electron has basically moved positive charges towards it. And so what that does is any other electron nearby that is attracted to that positive density that it sees. And so this attraction creates what we know of as electron pairs, and specifically Cooper pairs. So that pair of electrons from this attraction is referred to as a Cooper pair. And so as they move through the lattice, they have this attraction, and that is what gives us our superconducting properties, is that this attraction and this moving together of electrons through the lattice. And so let's go over some sort of numbers that maybe help you illustrate the attraction and so forth here. So the binding force that holds these things together is really small. So for low temperature superconductors, we're talking less than 1 milli-electron volt. So very small amount of energy holding this together. For high temperature superconductors, that energy is closer to 10 milli-electron volts. So it's higher, but it's still pretty low, right? So that explains why these low temperatures are needed, right? Otherwise, you would have thermal vibrations that would basically distort this binding force that's been created. And so that's why we need these low temperatures, so this binding force is enough to hold these electrons together and go through the material without interference. And so it can only happen at really low temperatures. All right, so some other things that you might be wondering about in terms of these pairs. So these pairs are moving through the lattice together, but the separation distance of these Cooper pair electrons can actually be quite large. And so for those low temperature superconductors, the separation can be up to 100 nanometers. So that's quite large when you're talking about an electron. But on the other hand, the high temperature superconductors, that distance is much smaller. So it's closer to 10 nanometers. And so when we compare the two classes, low temperature and high temperature superconductors are much more affected by defects in the lattice, right? So if we have a lattice defect that's more on the order of 10 nanometers, right, that can affect the binding of these electrons, and therefore defects in these ceramics, these high temperature superconductors, can greatly affect the superconducting properties. All right, so let's look at some different superconductors that are out there and look at the critical temperatures. So this plot, and I believe this is just from Wikipedia showing some of the critical temperatures from various ceramic structures. But a couple things to note here The first material that you see, yttrium barium 2 copper 307. So that's our YBCO, right? So it's a 1, 2, 3 compound of those cations. And so the critical temperature is 92 K. You may have found something slightly different. What we can actually see with this structure is that we can actually vary the critical temperature. So even if you got something different from a different source, that's okay. The structure is orthorhombic, and so that kind of gives us some basic information. So one of the kind of points that they make about the other components, and if you look through all of these, you'll notice some trends in these materials. So all of these contain copper. There's different other cations involved, but all of them have copper and oxygen. And so what we're going to see with the next part is the structure, and the amount of copper oxygen in the structure has a great influence on the properties. All right, so here's the structure. I don't expect you to memorize this structure or anything like that, but I want us to sort of go through the main parts and see if we can take away some of the theories on why YBCO is such a good superconductor. All right, so again, I mentioned the presence of copper and oxygen. So here, it's important to note there's actually two different states of copper in this structure. We have these more ribbon-like clusters where we have a central copper and it's surrounded by 4 oxygens. And then we also have these copper planes where it's coordinated by 5 oxygens. So we have these kind of 2 different types of copper regions in the structure. We also have, obviously, barium and yttrium inside this plane. And so I think I've mentioned this before, maybe in 403, but this structure is based on perovskite. The only difference, though, is that we have more cations. So we have barium, yttrium, and copper. And so that's why this structure is so tall, right? Because we have barium and yttrium, and they're in very specific sites in this structure. But it's based upon a perovskite structure that gives us this interesting properties. All right, so let's go to a next slide here. So this is showing the same structure where we have those planes and, the ribbons up here and then the planes down here. And so the Cooper pairs, what give us superconductivity, we can explain with this structure. And I just want to point out here that this is still theory. There's a lot of research going on into the mechanism, so it's not still fully understood, but this is one thought on the process here. So I also won't belabor the point because, again, this at some point could be proved wrong, and so I just want to sort of give you one of the theories in how this takes place. So the superconductivity takes place in those CuO2 planes. So we're talking about the coordinated by 5. So that's where the superconductivity happens. And then the other forms, the ribbons, the CuO versions, they act as sort of charge reservoirs. So that's where the charge is coming from. So our charge carriers, in this case, are actually holes. But we get those charge carriers by doping the structure. And we do that by adding more and more oxygen. So you'll probably notice in the YBCO structure, you always saw that 7 minus delta. That's because the amount of oxygen in that structure can vary. And so in this case, this would tell us that we're going to have more charge carriers the more oxygen we dope in. So this is also one of the reasons why we are going to titrate during this lab experiment to be able to determine how much oxygen content we have in that structure. So back to this. So we get these charge carriers by doping the structure with more oxygen. And so it enters as an anion, so O2 minus. It forms those chains, so the CuO chain, so up here. And then the electrons removed from those, and then for charge balance. And then it has a remaining hole, and these holes are mobile. And so that's what actually forms the copper pairs below the temperature. And so in this case, instead of the Cooper pairs of electrons, we're actually talking about Cooper pairs of electron holes. So that's kind of what is different. So even though we can look at that BCS theory to for metals, obviously there are going to be some differences for a high temperature, and like I said, it's still a little bit undetermined what is truly happening with these structures. But it's very clear that more oxygen is a better superconductor, and then copper is strongly, the different states of copper are strongly related to this formation as well. All right, so all of this in terms of the properties, right? We talked about these are the things that define a superconductor. But as we've seen, these high temperature superconductors are ceramics. And because they're ceramics, they are limited by the limitations of ceramics. And so that really falls back on processing. So that's the first part of this lab, is to actually synthesize and process the powder and form pellets. And so you can kind of see during that process, there's lots of limitations and things that can affect the properties. And because they're ceramics, and most ceramics are inherently brittle, that also has an effect on the applications, right? So just imagine we're trying to make, for example, electric wire, right? So with a metal, that's no problem. It's ductile. It can be shaped easily and formed easily. But if we have a ceramic now, it's much harder to process that, especially into a wire, and then it's brittle, right? It's going to fracture like the image I'm showing here of a plate. And so that makes it inherently bad for these applications. And so these things have to be overcome to be able to use these, and that's one of the main reasons why there is not a large usage of these high temperature superconductors. There are special applications, but they have to sort of account for processing limitations and the inherent brittleness. So those are challenges that we definitely want to fix if we're going to use these in the future.